Okay, everyone, we are ready to begin the summer school. I think after these incredible welcoming remarks from all our distinguished guests, I hope you all have some sense of just the significance and the impact of being here and what that represents. This comes with a lot of expectations. I think you can hear that in the remarks. But that, of course, implies that we have to meet those expectations, both through the participation in the school as well as the lectures that we are going to present to you. So that is why it is absolutely a pleasure to introduce our opening keynote speaker, Professor John Preskill from the California Institute of Technology. John Preskill is the Richard P. Feynman Professor of Theoretical Physics at Caltech, as well as the Director for the Institute for Quantum Information and Matter. His research career began in particle physics and cosmology, but I think as many of you will recognize, he now has a very strong interest in the field of quantum information, especially how we can use quantum computers to understand the fundamental physics of the universe. He is a member of the National Academy of Sciences, a fellow of the American Physical Society, and most recently, a recipient of the 2024 John Stuart Bell Prize for his seminal work at the interface of efficient learning and processing of quantum information. So please join me in welcoming Professor Preskill to the stage.
There we go. All right, well, thank you very much, Travis. I'm honored to be here. I hope you're all excited about the immersive experience that's about to ensue for the next 2 weeks. The topic of the school is quantum information science, and that's a broad topic which has many aspects which we've already been hearing about this morning. Quantum sensing using quantum strategies to improve the sensitivity, spatial resolution, the non-invasiveness of measurements, quantum cryptography using principles of fundamental physics to protect our privacy, quantum networking with the goal of distributing quantumness over long distances, quantum simulation to probe exotic many-body quantum phenomena, and quantum computing to speed up solutions to hard problems. I'm going to talk mostly about simulation and computing, but also make remarks about the other things. It's notable that the formidable hardware challenges that we're facing cut across these different application areas, so they build on one another and advance together. And what's particularly important to me as a physicist about quantum information is it provides us with concepts and ideas like entanglement, quantum error correction, quantum computational complexity, which help us to understand the physical world more deeply. From my point of view, quantum information science is in the early stages of the exploration of a new frontier of the physical sciences, what we could call the entanglement frontier or complexity frontier. That's different than the short distance frontier we explore in fundamental particle physics or the long distance frontier of early universe cosmology, areas I've worked in early in my career. But like those, the entanglement frontier is very fundamental and exciting. We are acquiring and perfecting the ability to create and precisely control very complex states of matter, states of many qubits that are highly entangled, that are so complex that we can't simulate them with the most powerful conventional computers we have or understand their properties very well with existing theoretical ideas. And that opens great opportunities for discovery. Our conviction that this is a fruitful frontier to explore rests largely on two ideas. Quantum complexity, our basis for thinking that quantum computing will be powerful and useful, and quantum error correction, our basis for believing that we can scale up quantum systems to large computers that can solve problems that would otherwise be too hard to solve. And both of those ideas rest on the underlying concept of quantum entanglement. That's the word we use for characteristic correlations among parts of a quantum system that are different from the correlations we normally encounter. You might think about it this way. Imagine a book which is 100 pages long. And if it's a conventional book written in bits, every time you read one of the 100 pages, you learn about 1% of the information content of the book. And after you've read all the pages one at a time, you know everything that's in the book. But suppose instead it's a quantum book written in qubits instead of ordinary bits, and the pages are highly entangled with one another. That means each time you look at a page, you just see random gibberish, which tells you almost nothing about the information content of the book. And even after you've read every one of the pages one by one, you still know almost nothing about what's in the book. And that's because in the highly entangled quantum book, the information isn't written on individual pages. It's encoded almost entirely in the correlations among the pages. And if you want to read the book, you have to make a collective observation of many pages at once. That's the essence of quantum entanglement. Very different from notions of correlation that we encounter in ordinary experience. And what's interesting about these quantum correlations is that they're very complex to describe in conventional language. Highly entangled quantum systems speak a different language than what we understand or our computers understand. So if you try to translate that quantum language to bits, you can't do so efficiently. In fact, if you wanted to completely describe all the correlations among a few hundred qubits in a very highly entangled state, you'd have to write down more bits than the number of atoms in the visible universe, and that's never going to be possible. Now, that in itself doesn't mean that by manipulating many particle quantum systems that we can do useful things, but we do have reasons for thinking that quantum computing will be powerful and will have important applications. For one, we know of some problems which we have good reason to believe are hard to solve using conventional computers, but theoretically, quantum computers would be able to solve them efficiently. The example we know best is the problem of finding the prime factors of a large composite integer. And people think factoring is hard classically because really smart people have been trying for decades to come up with better factoring algorithms, but still the best ones we have a runtime which is super polynomial in the number of digits in the number we wish to factor. But maybe most tellingly, we just don't know how to simulate with a conventional computer what a quantum computer does efficiently. And that's not for lack of trying. Physicists and chemists have been trying for decades to come up with better algorithms for simulating on conventional computers, highly entangled quantum systems. And still, the best algorithms that we have in the hardest instances have a runtime which is exponential in the size of the quantum system in the number of qubits. We don't think that the power of a quantum computer will be unlimited. We don't expect, for example, that a quantum computer will be able to find exact solutions to the hardest instances of combinatorial optimization problems. But it's notable and important that we think there are problems which are too hard to solve with conventional computers, can be solved efficiently with quantum computers. So it's a compelling question. What are these problems that are classically hard and quantumly easy? And we've learned important things about that in the last 30 years. I think there's still a great deal more to learn, and that when we have powerful quantum computers, that will accelerate the discovery of new applications. But if you're a physicist, there's a natural place to look for such problems because we expect that with a quantum computer, we'll be able to efficiently simulate any process that occurs in nature. We don't think that's true of conventional computers, which can't, as far as we know, efficiently simulate very highly entangled quantum matter. So we expect eventually to be able to use a quantum computer to probe more deeply into the properties of complex molecules and novel materials, and also to explore fundamental physics in new ways, say by simulating high-energy collisions of elementary particles, or the quantum behavior of a black hole, or what happened in the early universe right after the Big Bang. Now, the idea that we can use a quantum computer for such applications isn't new. Feynman articulated it over 40 years ago. And quantum computers are just now getting to the point where they're capable of doing interesting things. So evidently, quantum computing is difficult. And what makes it difficult is that in a quantum computer, we want a system that simultaneously satisfies a set of criteria, which are hard to make compatible with one another. We want our qubits to interact strongly with one another so we can rapidly process the information encoded in the qubits. We don't want the qubits to interact with the outside world, which can cause a quantum computer to fail. But we do want to be able to control the computer from the outside and eventually measure the qubits to read out a result. And it's quite difficult to build a quantum platform that simultaneously satisfies these desiderata. So it's taken decades to get as far as we have. So why do I say that we don't want the quantum computer to interact with its environment? It's because of a fundamental difference between quantum information and ordinary information, that we can't observe a quantum state without disturbing it in some uncontrollable way. That's not true of classical data. It is true of quantum states. And in the case of a quantum computer, if information that's being processed leaks to the outside world, that's the process we call decoherence. We might not observe that information ourselves when it's outside the quantum computer, but because in principle we could, that's just as bad. And that phenomenon of decoherence causes a quantum computer to lose its quantumness and lose its power. So if we want a large-scale quantum computer to solve hard problems, we will need the information that it's processing to be almost perfectly isolated from the outside world. And that's really difficult because our hardware is never going to be perfect. But we've understood in principle how to achieve that goal, keeping the quantum computer isolated from the outside using the idea we call quantum error correction. And the essential idea is that if we want to protect quantum information from damage, we should encode it in a very non-local way in a very highly entangled state. So when the environment interacts with the parts of the system one at a time, then just like that 100-page book I described earlier, the environment can't acquire information that's being processed by the computer. And we've understood how to efficiently process quantum information that's encoded in that very highly entangled form. And that's how we think the powerful quantum computers of the future will operate. There are a number of different approaches to building quantum hardware that are steadily advancing. Qubits can be instantiated in many different physical ways. We could, for example, encode a qubit in a single photon, which is in either one of two optical modes, or a single electron, which has a spin which points up or down along some axis, or a single atom, which is in either its ground state, its lowest energy state, or some long-lived excited state. Those are all remarkable encodings because the information we're processing is being carried by very simple single quantum systems, a single photon, a single electron, a single atom. And yet, in recent decades, we've learned how to control those systems reasonably well. Or a qubit could be encoded in a more complex system like an electrical circuit that conducts electricity without resistance at very low temperature, which is also remarkable because in that case, the qubit is encoded in the collective motion of billions of pairs of electrons, and yet we can make use of it for information processing purposes as though it were a single atom. It's important that we continue to develop these different approaches in parallel, as we don't have a clear idea yet of what hardware approach has the best prospects for scaling up to large systems that can really solve hard problems. And it may be some hybrid of different technologies, which is best suited for some purposes. Perhaps the two leading hardware approaches today are trapped ions and superconducting circuits. In the case of ions, there are several different modalities of operation, but in one, we can trap tens of qubits using electromagnetic fields in a linear array. And then with a very stable laser, we can precisely prepare initial states of those atomic qubits and perform single qubit gates with laser pulses and read out the qubits using lasers. But as in all the technologies, the key thing is to be able to do entangling gates acting on pairs of qubits. And in the case of the ion trap, that is done by taking advantage of the modes of vibration of the ions in the trap. And in the case of these linear arrays, we can perform all-to-all two-qubit gates. That is, any pair of qubits in the trap can be acted upon by a two-qubit gate. And it takes tens of microseconds to apply such a gate. To scale these systems up, we envision having many modular traps, which are connected together either optically or by shuttling ions back and forth without losing coherence. In the case of superconducting circuits for quantum computing, we now have systems with over 100 qubits in a two-dimensional array with nearest neighbors coupling in the array. Typically, those qubits are what we call transmons, which are in effect artificial atoms. They have to be very carefully fabricated and frequently calibrated. Now we can use a microwave resonator to read them out, microwave pulses for the single qubit gates. And for the two qubit gates, they can be done in various ways. For example, by tuning the superconducting circuit elements, bringing transmon qubits into resonance with one another, for example, and two qubit gates can be performed in tens of nanoseconds. For scaling up, things that will be helpful will be achieving modular architectures, reducing the number of microwave control lines, better materials for the qubits, better fabrication, perhaps alternative qubit designs, among other things. Now, really, the watchword of quantum information science, at least as it pertains to quantum computing, is we believe that quantum systems cannot in general simulate, or classical systems cannot in general simulate what quantum systems do efficiently. I think that's about the most interesting thing that's been said about what's different between quantum and classical. And so we're strongly incentivized to validate that in experiments to the extent that we can. Already almost 5 years ago, the Google Quantum AI team announced they had demonstrated quantum advantage using a superconducting processor. And more recently, those demonstrations have been improved. They built a device called Sycamore based on superconducting technology. In its more recent version, there are 67 working qubits laid out in a two-dimensional array with nearest neighbor couplings. And they performed up to 32 layers of two-qubit gates on those qubits. Now, it's a noisy device, so if you perform that sequence of layers and then measure all the qubits, most of the time you just get useless random junk, but maybe 1 in 1,000 times or a little better, you get a useful signal. And then the computation can be repeated millions of times in just a few minutes to extract some statistically valid result. Now, simulating a device like Sycamore with a classical computer is quite challenging, and the cost of doing so continues to grow exponentially as we increase the number of qubits. Now, the particular algorithm run by Sycamore, which was a random quantum circuit, is not of much practical value except for the purpose of demonstrating the superiority of the quantum device over classical computers. But this is still a noteworthy milestone. It indicates that now we have quantum hardware which works well enough to produce meaningful results in the regime where classical simulation of what the quantum computer does is difficult. Well, it's useful to have a word for the era of quantum information processing we have entered. The word NISQ has caught on. It's an acronym and means Noisy Intermediate Scale Quantum. Intermediate scale, to remind us that these are devices with a sufficient number of qubits that we can't, by brute force, simulate what the quantum device does with the most powerful existing supercomputers, including the one here at Oak Ridge. Noisy reminds us that these devices are not error-corrected, and the noise is a serious limitation on their computational power, on how large a quantum computation can be executed correctly. Now, to physicists, NISQ is quite exciting. It means we now have a tool for exploring the physics of many entangled qubits in a regime that we've never had experimental access to before. And NISQ might have practical applications of economic value. But we're not sure about that. We should view NISQ as not something that will change the world by itself, but a step towards the more powerful quantum technologies we're hoping to develop in the future. One way in which we might make use of a NISQ computer is a kind of hybrid quantum classical scheme. It makes sense to use our powerful classical computers to the extent that we can, and then try to boost that power using a quantum coprocessor. One way it might work is this. We perform a quantum computation of modest scale, measure all the qubits, then feed the results to a classical computer, which returns instructions to slightly modify the quantum computation. And that cycle is repeated until convergence, where the goal is to find some approximate solution to an optimization problem. Now, as I said, we don't expect quantum computers to be able to efficiently find exact solutions to the hardest instances of combinatorial optimization problems, but they might be able to find better approximate solutions or find them faster than classical processors. So should we expect that in the NISQ era, quantum computers will be able to outperform classical systems running the best algorithms for solving the same problems? Well, we don't really know. We can try it and see how well it works, but it's really a lot to ask because those classical optimizers are well honed over decades of development, and the quantum processors are just becoming available in the last couple of years. I think a fair assessment is this, as far as where NISQ stands now. NISQ is already valuable for scientific exploration, but there isn't a proposed application of NISQ computing with commercial value for which quantum advantage has been demonstrated if we make a fair comparison to the best classical hardware running the best algorithms for solving the same problems. And we don't currently have persuasive theoretical arguments indicating that commercially viable applications will be found that don't use quantum error correcting codes and fault-tolerant quantum computing, though of course they might be found. To dig a little deeper into quantum applications, there's a useful survey of quantum algorithms that recently appeared that went over many of the known algorithms and did some rough estimates of the resources needed to run end-to-end applications. And of course, it's not the final word on the subject. Our understanding of quantum algorithms steadily advances, but it's a snapshot of where things are now, and it's kind of sobering. There are applications of quantum computing to problems in optimization and finance and machine learning. In most cases, the quantum speed up that we can expect for those applications is at best quadratic. That is, the time to run on a quantum computer scales like the square root of the time on a classical computer. So quantum advantage will only kick in for very large problem instances and correspondingly very deep quantum circuits. Now, the applications to quantum many body systems, to chemistry and materials, look more promising. But even there, we'll need hundreds of very well-protected logical qubits protected by quantum error correction, and we think at least hundreds of millions of very high-fidelity logical operations will need to be performed on those qubits to outperform what classical computers can do. So either way, quantum fault tolerance seems to be needed to run these applications, and that has a high cost in the number of physical qubits that we'll need and the number of gates that we'll need. And incidentally, it's important also to follow the speed of the error-corrected quantum computer. There are big differences among different hardware platforms in how fast they can do error-corrected operations, and that's going to be important. It's going to make a difference whether running an application takes 1 day or 1 year. It was already pointed out in the very early days of quantum mechanics that in a sense we have a theory of everything that matters in everyday life. It's the Schrödinger equation describing electrons interacting with one another electromagnetically and with atomic nuclei. That underlies everything in chemistry and materials science. The trouble is that when there are many electrons, the equations are just too hard to solve. Dirac pointed that out. For some reason, it took 50 years for Feynman to say, well, the right thing to do then is to solve these problems using a quantum computer, a different type of computer. Now, for understandable reasons, there's a lot of enthusiasm now for using artificial intelligence to solve these many electron problems. And I think that is promising and will be fruitful. But what AI does is it generalizes from the things we know to make predictions about situations we haven't encountered before. And for that, we need a lot of suitable training data. And I think an important role for quantum computing in the decades ahead will be to provide that training data which AI can leverage for solving many electron problems. So let's talk about finding properties of ground states of many electron systems. That's where a lot of the computing power is focused today in computational quantum chemistry, for example. Dirac said the equations are too complicated to be solvable when we have many electrons. He was thinking of like 10 electrons. But that's not quite fair because we solve it all the time. We have, for many cases of practical interest, heuristic classical algorithms which perform well at solving these problems. So with quantum computing, we are targeting that, at least relatively small today, corner of computational chemistry and materials science that deals with strongly correlated systems, which is really the same thing as highly entangled. So what we're interested in is, can quantum computers efficiently solve for ground states and the properties of ground states in the cases where those classical methods don't succeed? And in fact, we know quantum computers, or we strongly believe quantum computers can't always solve ground state problems for some Hamiltonians. Well, that's okay. We think the cases where a quantum computer can solve the problem efficiently are cases where nature can't solve it either. So those are ground states that don't actually occur under realistic physical conditions in the field or in the lab. But the key question is, how useful are quantum computers for the physically relevant situations that are beyond the reach of classical methods? Of course, what we mean by physically relevant is a little fuzzy there. So in ground state chemistry and materials, as in other areas of applications of quantum computing to the physical sciences, we're looking for problems that are quantumly easy, classically hard, and physically relevant. So we have all these classical methods for solving many electron problems in particular. They often work, but they don't come with performance guarantees, and they can fail in some cases. As far as we can tell, and it's not possible to make a precise statement about this, but for materials and molecules that we are interested in for practical reasons, the classical methods don't scale exponentially. They scale like some high power of the number of electrons or the number of orbitals. But of course, that still makes it infeasible for large molecules. Now, the quantum algorithms are heuristic also. They're not guaranteed to work. What a quantum computer is really good at is measuring the energy of a many qubit system and projecting onto an energy eigenstate. So if we want to use that to learn about ground state properties, we have to be able to prepare a state which is a pretty good approximation to the ground state, which has some sizable overlap with the ground state. And it's not guaranteed in general that we can do that. In some cases, we probably can't. I think what's a reasonable expectation is that in ground state chemistry and materials, there is quantum advantage. It's not exponential, but it's a significant polynomial advantage. That is, the classical runtime is some high power of the quantum runtime, and that's good enough to have a big practical impact eventually. But it seems that we'll need fault-tolerant quantum computers to take advantage of that opportunity, and that has a high cost in the number of qubits and gates that we'll need. I'll come back to the cost of quantum error correction a little later. Now, we don't only have to talk about ground states in considering applications of quantum computing to physical systems. We might be interested in simulating dynamics. That's a real opportunity. Classical computers are very bad at simulating the dynamics of a many qubit system. When the system becomes highly entangled, quantum computers should be able to do that. But if you're a skeptic, you could say, well, you know, what's really interesting to do with simulations of dynamics on a quantum computer? In some cases, we think quantum many-body systems are well localized. That means they don't get so highly entangled. In that case, maybe a classical computer can simulate them pretty well. In some cases, they do become highly entangled. For example, when we have a system with strong quantum chaos, they become highly entangled very quickly. Classical algorithms fail. But does something interesting happen? What typically happens in a highly chaotic quantum system is it converges to thermal equilibrium pretty quickly. And after that, not much seems to be happening. But I think the answer is we have to ask the right questions, and we should be prepared for surprises when we start simulating dynamics in regimes that we haven't had access to before. And that's already been happening. We've seen instances in quantum simulation where quantum systems behave differently than expected, where they behaved less chaotically than people thought, or where adiabatic evolution failed in regimes when people thought it would succeed. And in some cases, you find out after the fact, oh, I could have simulated that classically, but that doesn't mean the quantum computer wasn't useful. It led you to a discovery which then focused your attention on a problem that you might have been able to solve theoretically or with classical computation. That's progress. I should probably emphasize the distinction between digital and analog quantum computation. By digital, I mean using a universal quantum computer, which can be used to run any quantum algorithm, not just simulation, versus analog simulation, by which we usually mean some quantum system which is to some extent programmable, which is described by a Hamiltonian, which resembles a model Hamiltonian that we'd like to be able to study. Analog quantum computation has been an active area for a few decades now, particularly with ultra-cold atoms. Digital quantum simulation is really just starting to come up to speed. Digital has some advantages. It means we have more flexibility in the Hamiltonians we can study, in the initial states that we can prepare. But the gate-based simulations of time evolution tend to be very expensive, require a lot of gates. The platforms that we use for analog and digital simulation are pretty much the same. They're just used differently, like ultra-cold atoms and trapped ions and superconducting circuits. So the two approaches will advance together. They're becoming more sophisticated and controllable, but the analog simulators have limitations because we can't control them perfectly. They are best suited for studying properties that are sufficiently robust that even in a noisy situation, we can study them fruitfully. We can anticipate that, as happened with classical computing, analog quantum algorithms will eventually become obsolete because they can't be error corrected the way digital quantum computations can be. But that might not happen for decades. So analog quantum simulation is going to be a tool for discovery probably for some time. For the time being, the digital simulators that we can run on circuit-based quantum computers today will be laying foundations for fault tolerance simulations that we expect to be able to do further in the future. So what do I mean by simulating quantum dynamics? Typically, we mean following this protocol. We prepare some initial state on the quantum computer. We simulate its evolution as described by some many-qubit Hamiltonian for a while, and then we measure an observable. And the goal of the algorithm is to sample accurately from the probability distribution of that final measurement. And what theorists can do today is they can try to determine the cost of such an algorithm. The cost usually meaning the number of qubits we need, the number of gates, and that cost depends on many parameters: the accuracy we're trying to achieve, the size of the system we're simulating, the number of particles, the total energy, and other things. And in many cases, we can argue that at least on a quantum computer that scales polynomially in all these parameters, which we can call efficient, it doesn't necessarily mean practical, depending on the details of that polynomial scaling. An important point is we need to be able to efficiently prepare the initial state that we're interested in. And that's where a lot of the conceptual thought needs to focus in thinking about simulation of dynamics. Can we efficiently prepare interesting initial states that we want to study? Sometimes in simulation algorithms, we're trying to simulate continuous variable systems. We need to encode those in qubits, which means we have to discretize the problem, and that also has some cost we need to keep track of. Well, I have this background in particle physics and quantum field theory. It's a little striking to me to think that it was 50 years ago, just around the time I was starting graduate school, that one of my scientific heroes, Ken Wilson, proposed that we can study quantum chromodynamics using conventional computers by putting the theory on a lattice. And that was exciting, but it was clear at the time that it was going to be a while before we had the computational power and the theoretical methods for taking advantage of that opportunity. And that was the case. A lot of visionary people got to work on lattice gauge theory, simulating properties, computing properties of QCD using conventional computers. It's a good thing they did. It might have taken about 30 years for the results to start to be informative for the high energy physics research program, but it did eventually happen. And now the lattice gauge theory calculations are an important part of connecting high energy physics experiments to theory. There are some things that we can't do with those simulations, which take place in imaginary time, not in real time. At least we can't do them efficiently, like simulate real-time collisions at high energy of elementary particles, or how nuclear matter behaves early in the universe or inside neutron stars. So those are opportunities for quantum computing, but keep in mind the time scale. It's 50 years since people started working on conventional computers applied to QCD. It's going to be a couple of decades, probably, maybe longer, before we really get useful information about quantum chromodynamics from quantum computers. It gets classically hard to study the theory when we consider processes that produce highly entangled states, like high energy collisions, or when there are many fermions, like in nuclear matter. So for the time being, simulating quantum field theory, I think it's a exciting thing to be doing. It's very much in the wheelhouse of the DOE Office of Science, but we're really laying foundations for more revealing work we hope to do in the future. An important part of it is that we learn things by thinking about and trying putting particle physics on a quantum computer. That happened for conventional lattice gauge theory simulations. We understand quantum field theory better because people thought hard about how to study it with computers. And that's going to be true for quantum computers too. All right, let's talk about noise. Quantum computers today are noisy. There are methods for mitigating the noise, which are actually essential to get useful results out of the processors that we have now. Roughly speaking, they work by characterizing the noise well enough so we can do some post-processing to get improved results than the raw results of the quantum computation. But the asymptotic cost of the mitigation methods that we use today, although they do work, is exponential. So it won't be practical as the number of qubits scales upward. Quantum error correction scales much better asymptotically, but it's not useful today in the current processors. Why is that? Well, for one thing, we need better 2-qubit gate fidelities. We need a lot more physical qubits. We need the ability to control very large systems. We don't have those things now. And you also need things like fast measurements, the ability to feed forward measurement results to reset qubits rapidly, and so on. All important technical capabilities to advance. So to get an idea of the resource cost of quantum computing, when it's error corrected, consider the surface code, which is probably going to be the first quantum error correction method, which is for which we get some practical advantage. The surface code has some nice features. It can tolerate relatively high noise compared to other codes, and we only need local processing in a 2-dimensional array to make use of it. Once the error rate per 2-qubit gate is less than a so-called threshold of accuracy, as we increase the distance of the code, which is a measure of how many errors it can correct, the logical error probability decays exponentially as the distance increases. And in the surface code, the distance goes like the square root of the number of physical qubits in the code block. That threshold of accuracy is about 1%. So suppose we have a probability of error per 2-qubit gate that's a factor of 10 better than that, 0.1%. We don't really have that quite in multi-qubit devices now, but maybe we will in the next few years. And suppose we want a logical error rate per gate of about 10 to the minus 11, what we might need to start to see quantum advantage in quantum simulation algorithms. Well, look, we're trying to get the logical error rate better than the physical error rate by 8 orders of magnitude. We're not going to do that by making better hardware. We're going to have to use quantum error correction. Just looking at this formula, that means we need a distance of 19. The number of physical qubits is the square of the distance, and then we need a comparable number of physical qubits to help read out the error syndromes. So we need about 1,000 physical qubits per logical qubit. And things get better as we improve the physical error rate, improve it by another factor of 10, and then we're down to distance 9. Now we just need a couple hundred physical qubits, but that's still a lot. So there has been a lot of progress towards quantum error correction in the last couple of years. I want to say something about that, and these are a few of the areas in which progress has been achieved, which I'll quickly mention. Okay, first, error conversion. What does it mean? Erasure conversion, sorry. Well, we would like, if possible, to know where errors occur in a quantum computer, on which qubits and in which time step. If we know where the errors are, we can do error correction better. So here's a simple example. Suppose I'm trying to protect a classical bit against bit flips. I use a repetition code. I encode it in n bits that are either all zeros or all ones. And then if some of the bits flip, I can do majority voting to decode correctly, and that works if fewer than half the bits flip. But suppose I knew which bits had flipped, then I can just look at any unflipped bit in order to read out the result. In quantum error correction, it's a little more complicated than that, but the same principle applies. If you know where the errors occur, then you can do error correction more efficiently and more effectively. And in some cases, you can engineer in the feature that the dominant errors, not quite all the errors, but the dominant errors are ones that you detect. One way of doing that is using Rydberg atoms. Here, we're holding atoms using optical tweezers. And the main source of error is that you excite the atoms to highly excited states so they can interact strongly with one another because they're large dipole moments. And the main source of error is the spontaneous decay of that highly excited state. But if you use the right atom and encoding, you can arrange that spontaneous decay error doesn't take a 1, the excited state, to a 0, the low energy state, but to some other state that you can detect. So most of the time you can tell when an error occurs if you can measure the occupation number of that state G without disturbing the coherence of a superposition of the 0 and 1. Another version of the idea in superconducting circuits is you can use 2 transmons or 2 resonators and encode a qubit in the 0-1 state and the 1-0 state. That is, 1 transmon excited, 1 not excited, or the other way around. And the dominant error is spontaneous decay, again, of the 1 to the 0. If you can detect that the state is 0, 0, then you know an error has occurred. If you want to do that without disturbing the coherence of a superposition of 0, 1, and 1, 0, and that's been recently demonstrated. Another helpful idea is bias noise, or taking advantage of the structure of the noise to make quantum error correction more efficient. Suppose we have a way of physically suppressing the bit flips. So the dominant error, bit flips are still there, but at a reduced rate. The dominant errors are the phase errors, which are flips in the conjugate basis. That can make error correction easier. We can focus our error correcting power on the dominant phase errors and not worry so much about the bit flips. For that idea to work in a computation, we need to be able to perform gates that preserve the bias. We don't want to do gates that will transform the errors that occur frequently, the phase errors, into the bit errors that we don't have to want to worry about, the bit flip errors. And it was only realized a few years ago that there's a nice way of doing bias preserving gates using continuous variable encodings of qubits. So by that I mean we can consider a harmonic oscillator like a microwave resonator in a superconducting circuit, and we can encode a qubit in a so-called cat state. That means it's a coherent state, a displaced ground state of the oscillator, which is either displaced to the left or displaced to the right. Make those far apart from one another, and a bit flip that changes the state way on the right to the state way on the left, that becomes exponentially suppressed in the number of photons in the oscillator, the number of the occupation number of the oscillator. So we only have to worry about the bit flips, or sorry, about the phase errors, and those only increase linearly with the displacement in phase space. That's been recently demonstrated. The bit flips becomes suppressed exponentially as we increase the mean photon number. And so we should be able to use just a repetition code to take care of the phase errors. And people are working on that, and we'll probably hear more about it in the coming year. Another important development is we have better codes, better in the sense that they're more efficient. In fact, there are constant rate quantum codes where the number of protected qubits scales linearly with the total number of physical qubits, and also constant rate codes that have the distance which scales linearly with the number of physical qubits. The number of errors we can correct scales linearly. That's a lot better than the surface code, for which the distance scales like the square root of the number of physical qubits. And we've learned that codes of this type can have high accuracy thresholds. They can tolerate pretty high noise. we can efficiently decode them. Now, we also need to be able to do processing of the encoded information, and people are making progress on that in recent months. The catch is that to measure the error syndromes for these more efficient codes, we have to do geometrically non-local operations. We can't use only nearest neighbor processing in a two-dimensional array like we can for the surface code. So we need those long-range gates, which we can achieve by moving qubits around or having some long-range couplings in the quantum computer. An example of the kind of improvement you can get is a recently discovered code with 144 physical qubits, which has 12 protected logical qubits and a distance of 12. For the surface code with a distance of 12, that also has 144 physical qubits in the block, but it just protects a single logical qubit. That's a big improvement in coding efficiency, if we can take advantage of that long-range processing. So what these examples show is we're really in an era of co-design where our theoretical ideas, for example, better codes, are leading people to think fresh about how the hardware should be designed. And correspondingly, we have features of the hardware that we can exploit in designing new codes. And that's going to continue to be important in the years ahead. It's a particularly exciting time for these Rydberg atom arrays, for neutral atoms that are held in optical tweezers. It's not to be unexpected that these systems will lead the progress in quantum error correction, at least for a while, if they can continue to improve their 2-qubit gate fidelities and make other improvements. These are systems now for which we can have thousands of physical qubits, and where the atoms can be moved by moving the tweezers around, by reconfiguring them, which enables the geometrically non-local operations and syndrome measurements that we want to take advantage of these more efficient codes. And in this arena, we can also use that idea of erasure conversion to make a lot of the errors detectable to improve the error correction. But there are caveats. We haven't yet seen in these systems many repeated rounds of syndrome measurement as we have in the superconducting arena. And people are working on that. That will probably require continually reloading fresh atoms into the system, and that's a technical capability people are trying to develop now. Now, there is a catch in the case of Rydberg and ion trap computation, that we have the advantage that we can move qubits around, and that means we're not necessarily restricted by geometric locality. But movement is slow. If you have an atom trapped in an optical tweezer, there's a limit to how rapidly you can accelerate that atom without shaking it loose. And that means if we're going to rely on movement, that slows down the clock speed appreciably. And also the readout has to be improved. The readout times are longer than we'd like, and people are working on those things. All right, I left you a few minutes to talk about quantum sensing and quantum networking. Quantum sensing is a quantum technology which is already having economic impact in contrast to quantum computing. What's a quantum sensor? It's a quantum thingy that senses something. Typically, that's a few-level quantum system, though it could be something more sophisticated. And what makes quantum sensing exciting is that there are quantum strategies that can improve sensitivity and spatial resolution and allow us to do less invasive measurement. So we can envision, say, using very sensitive magnetometers to monitor electromagnetic activity in living cells, see neurons fire. One approach to doing that is using nitrogen vacancy color centers in diamond and other related systems where you have an electron spin in proximity to a nuclear spin, and that system can be manipulated optically at room temperature. Quantum sensors have applications to positioning, navigation, and timing. They can give improvements in measuring acceleration and gravity gradients. for example. They can be used for looking for stuff underground, like water. One way of doing that is with atom interferometry, where we have a device which is sensitive to the relative phase picked up by an atom that follows either one of two possible paths in space-time. Quantum sensing can be used for detection of some dark matter candidates, for example, axions, which are viewed as a promising candidate to be the dark matter in galactic halos. There are various ways of looking for axions using superconducting technology, and quantum sensing can also be used to look for violations of fundamental symmetries like time reversal that can tell us about physics beyond the standard model. Now, to advance quantum sensing, we want a lot of the same things we want for quantum computing. We want better materials, more precise control, longer coherence times, more efficient readout, more compact devices, and probably most of all, new ideas about how to make use of quantum strategies to improve measurement. We can speak of next generation quantum sensing. That means improving sensitivity in particular by using more exotic quantum strategies like squeezing oscillators or entangling qubits. There is a trade-off if we enhance sensitivity by using such methods that can also enhance sensitivity to noise in the environment and reduce coherence time. So it's a delicate thing to find the right balance between improving sensitivity to the signal you want and not correspondingly increasing too much the sensitivity to noise. Maybe the most heroic example of quantum enhanced sensing in physics is LIGO, which can see colliding black holes from billions of light years away. And by injecting squeezed light to improve sensitivity into their interferometer, they can improve their sensitivity, have demonstrated improvements in sensitivity at about the factor of 2 level. That's a big deal because that increases by a factor of 8 the volume in which you can see events and the rate at which you see events. Maybe the most economically useful quantum sensing technology is atomic clocks. I mean, they have enormous economic benefit with the microwave clocks that are in widespread use today, for example, in the global positioning system. Optical atomic clocks are much more accurate, or at least potentially can be. And we're seeing improved precision by getting better control of systems of many atoms. That's going to continue. I mean, now you can actually detect, because there's precision at about the 10 to the minus 19 level, the change in the rate in which an atomic qubit ticks when you move it up or down by a millimeter in the Earth's gravitational field because of the gravitational redshift, and potentially orders of magnitude further improvement is possible if we have systems of many atoms we can control well. And if we can make entangled states, and we have to figure out better how to do this, in a sensing array where the sensors are physically distributed somehow on the Earth, that can improve Earth measurement, might lead to better predictions of earthquakes and volcanoes and so on, which would have economic benefit for sure. And maybe the most exciting thing is that we hope someday we will be able to have an array of telescopes on the Earth or maybe in solar orbit that share entanglement, can teleport photons back and forth. And so that telescope array will have extraordinarily good resolution, would be able to see details on the surfaces of exoplanets, at least if we have a source of light that's bright enough on the planet. Quantum networks. So we should distinguish 3 different types. Quantum networking can occur within a single quantum data center, because we're going to need modular designs as we scale quantum computing up. So we'll have multiple processors, and they have to be able to communicate quantumly with one another. That's a type of quantum network that we're really going to need to scale up quantum computing. We heard about point-to-point quantum communication on the scale of kilometers, which can be useful for generating secret keys that can be used for encrypted communication. And eventually, we'd like to distribute entanglement over much longer distances, for example, for some of those applications to sensing, and we might want to have at some point a quantum internet that allows quantum computers to communicate. Now, the way quantum networking is usually done is we need quantum information to travel. That is in the form of photons, typically traveling through optical fiber. There's loss in fiber, although people have tried hard to improve the loss. It hasn't changed much for 20 years. So you can kind of barely send a photon 100 kilometers, but sending it a few hundred kilometers is just impossible. If we want quantum networks on longer scales, one way is to make use of satellites. I think the one that's most important in the long run is we need quantum repeaters, which can extend the range of quantum communication. And that's quite different from the repeater technology we use in conventional optical communication now, which essentially measures the signal and resends it. You can't do that in a quantum network because if you measure it, you'll damage the signal. So you have to use instead a form of quantum error correction by which we share entanglement between nodes. The entanglement is between nodes. That entanglement is noisy, but there are entanglement purification protocols that can take a lot of noisy shared entanglement and transform it into higher fidelity entanglement, but with fewer entangled pairs. And that can be extended to long range. But that quantum repeater technology really doesn't exist now. People have been working on it for 20 years, but there hasn't been that much progress. So really, we need two things, particularly for application area 1 and 3. We need transduction, because if we're going to use flying qubits in the form of photons to connect nodes together, then we have to be able to coherently transform quantum information in a processor, like a superconducting processor, to photonic qubits, and then back again at the other end of a communication channel. And people are working on that too, but we have a long way to go. And we need the quantum repeaters. A cool thing about quantum communication networks is you don't necessarily, if you use a so-called device-independent protocol, have to trust the equipment that you're using. You could get it from your adversary, but by taking advantage of properties of entanglement, the violation of Bell inequalities in particular, you can verify that your equipment is working as intended, even if you don't trust its internal workings. And what are the applications? This is a big question about quantum networking. What's becoming practical now is point-to-point key exchange over, scales of kilometers. How much the world needs that, an open question. And eventually we can imagine other applications, but probably requiring longer range communication. Coming back to quantum computing, there are two big open questions that are confronting us. How are we going to scale up to quantum computers that can really solve those hard problems that are well beyond the reach of classical processors? And once we do so, what will be the most important applications for science and industry? I consider both questions to be wide open, which means you guys are going to figure it out. I do think it's an exciting time, and we're going to see a lot of remarkable developments in the next few years, or the lifetime of a graduate student career. We'll see significant progress toward fault-tolerant quantum computing, though we won't yet be in the regime where it's a practical use in running algorithms. We'll be getting closer. I do expect there will be scientific discoveries continuing to be made by using our quantum simulators, both analog and digital, and that we'll continue to make progress in quantum measurement through quantum strategies, in particular through better control of many qubit systems. So I think the story is there are very tempting opportunities in quantum information science. Fulfilling that potential is a great challenge, and we're going to need extraordinary advances in engineering and basic research to meet those challenges, and that's going to take time and effort, sustained, inspired effort and investment, probably over decades. So it's not going to be fast or easy, but it's going to be a lot of fun. And the good news for you guys is we've really only just begun, so most of the fun lies ahead. Well, thanks for listening.
Okay. Thank you, John. That was excellent. We have time for a few questions. We have some microphone runners around here. Where are my microphone runners at? Jared, were you? Yeah, if you could move the microphones over to here. I see. Here you go.
Thank you for the talk.
Mm-hmm.
So I was told once that the theory of what can be done on a real device will develop once we actually have real devices that are fault tolerant. But maybe I'm just not entirely convinced by this statement. So if I gave you a fault tolerant quantum computer and I just ask you, find me a new algorithm, something that you can do with a real quantum device that you can't do classically, how would you find such a thing? Even if you have a perfect device, I understand there's other things that you can learn from studying by building a quantum computer, but given a perfect one, how would you find new things that it can do?
All right, this is a very good question. The question is, one sometimes hears, I think you heard it from me today, that when powerful quantum computers are available, we expect that to accelerate the discovery of new applications. How's that going to work? If we had perfect quantum computers today, how would we figure out their applications by running them? Well, I don't know. But I would say that if you look at the history of classical computing, what has often happened is there have been heuristic ideas for algorithms where one could not, on theoretical grounds, guarantee that those algorithms would work effectively and be efficient. But when people started trying things, they discovered that they work better than expected. The simplex algorithm is an example. Eventually, people figured out, how to do linear programming on a theoretical basis. They could explain why it works well, but it was only by fooling around and experimenting that people realized that it's a good method. Look at look at machine learning now. Right? I mean, it's changing the world. We have very limited theoretical understanding of why we can efficiently train neural networks for applications people care about, but people tried it and it worked. So I'm anticipating developments like that. People, I think, will be bolder in the things that they try when we have the devices. Than they are when they're trying to do theoretical analysis of algorithms. And I think we will make significant improvements through experimentation on some of the ideas that we have now, in particular with quantum simulation. Some things may work better than, I hope, better than we can currently theoretically justify.
Thank you.
Thank you for the talk. So you mentioned the simulation of quantum gravity using quantum computers. So which reminds me a work a couple years ago, they are using a sycamore to simulate an XYK model, and they are mapping that using holographic duality to a classical gravitational effect. So I can only imagine this type of simulation in the lower energy limit. So how can it be possible to simulate higher energy gravitational effects like quantum gravity?
All right, so this is a question about simulating quantum gravity on quantum computers, which I didn't say out loud, but I did have it on my slide. It's something I'm actually excited about. You mentioned, first of all, that something that has already been discussed and in a modest way attempted on quantum computers is simulating something called the SYK model, which is maybe the simplest model we have of so-called holographic duality. It's just a system of fermions with all-to-all four-body interactions, which has a dual description in terms of simple 1+1 dimensional model of a black hole. And actually, I think that it will be interesting. We don't have the quantum computers capable of doing it in a scientifically informative way yet. But it will be interesting to simulate the SYK model, on larger scales, because there are some things we can compute, in particular in the limit of the number of fermions going to infinity, but there are a lot of properties of the SYK model which are actually hard to compute classically. You asked, well, what about high energy events in quantum gravity? I think that's a particularly interesting thing to study. In particular, what happens when you do a collision of particles with energy much larger than the Planck scale? We have limited ability to analyze that with the current understanding of quantum gravity. What I had in mind in that regard is we do have holographic duality still to lean on, so we can formulate a high energy collision in terms of a property of a dual theory, which isn't gravitational at all, which in principle we can simulate. And now exactly what the observables are to study and how to do this, the state preparation is a good theoretical problem. I mean, but I think I don't see any reason why it could not be done efficiently on a quantum computer to study very high energy graviton-graviton collisions using the dual description. And I think that's going to be exciting. We won't be able to do it for decades, though.
Thank you very much.
Hi, over here.
Hi.
I'm Kevin Mato from the Technical University of Munich, and I thank you very much for this amazing talk. It's not something that I would say it's not something happening every day. It's a nice overview. I just have a kind of a naive question. I just started with fault tolerance, error correcting codes, and fault tolerant implementations of quantum circuits. And I was wondering if you could just elaborate a little bit on what are, according to your opinion, the milestones that we should achieve to reach fault tolerant. Maybe if you could talk a little bit about roadmaps, since companies talk a lot about physical design roadmaps, but never about fault tolerant roadmaps. So if you could just elaborate a little bit on this. Thank you.
So the question is, what are the milestones in fault tolerant quantum computing that we should be shooting for? Well, the first one is we would like to see the following thing. So well, consider the surface code. I told you that as we increase the number of physical qubits, as we increase the distance, logical error rate should go down sharply. So that's the first thing we'd like to see. Google did publish a result where they compared the 3x3 surface code with 9 physical qubits with 5x5, 25 physical qubits, to see if they could get this just in quantum memory, not quantum processing, to see if they could get the memory time to improve with the larger code. And maybe it just worked a little, just barely worked. It was not very spectacular. I expect that in the next couple of years, we will see far more convincing demonstrations, both in superconducting and Rydberg atom experiments, of memory time improving a lot as we increase the size of the code block. If that doesn't work, that'll be very interesting because it'll mean there's some features of the noise we haven't taken properly into account, and we're going to have to, you know, figure out how to deal with that. But I mean, I think it really is, there's no guarantee it'll work, is part of what makes it interesting. It should work if, you know, our theoretical notions of the nature of the noise are correct, but maybe they're not. After that, we'd like to see logical gates improved significantly in fidelity using error correction. And again, I think we're going to see that in the next couple of years. It might first be done most convincingly with Rydberg atoms, but we'll see. Of course, then there's a big gap till the next milestone after that, which is to really run an algorithm that makes use of error correction, which either, you know, significantly outperforms what we can use with other noise mitigation methods, or maybe even solve something that's hard to solve classically. Those are all very important milestones.